Hello class, this is IR22532, your TA. Today I will talk about infrared spectroscopy. So there are several instrumental methods of determination of material characterization and chemical identification. You have nuclear magnetic resonance, NMR, and that's the excitation of the nucleus of atoms through radio frequency irradiation. NMR is, I think, the most exhaustive, the one that gives you the most information locally and in general throughout the molecule. There's also infrared spectroscopy, which is what we will be looking at today. And this is triggering. The way it works is by triggering molecular vibrations through irradiation with infrared light. It provides mostly information about the presence or absence of certain functional groups. And then you have mass spectrometry, and it's the bombardment of the sample with electrons, and therefore destroying the molecule into certain fragments, and their detection. It provides information about the molecular mass and the atom connectivity. And then you have ultraviolet spectroscopy, UV, and this works by the promotion of electrons to higher energy levels through irradiation of the molecule with ultraviolet light. It provides mostly information about the presence of conjugated P systems and the presence of double and triple bonds. Of these, I would say all of them are very useful, but NMR and IR are probably the most useful. IR spectroscopy. So IR deals with the interaction of infrared radiation with matter. The IR spectrum of a compound can provide important information about its chemical nature and molecular structure. So it works by measuring the absorption of IR radiation, although infrared emission and reflection are also used. Once we have our graphs, we'll be looking at actually the transmission, so the light that is not absorbed actually. So this is used for a lot of things. So mainly it's used by organic chemists for the analysis of their compounds. It's also useful for inorganic chemists and their organometallic compounds. So you can read this, or you can learn about this in physics. If you're planning to go to grad school, you should probably know this. Well, in science, whatever you're doing, if you want to be a forensic scientist or something along those lines, you should memorize the spectrum. This form of the spectrum as well. But notice IR is right here. It's between microwave and visible light, so it's a little bit in higher or lower frequency as the rest. Then you have these formulas again. Just know the relation between energy and frequency. As you increase the energy, frequency increases, but as you decrease wavelength, energy increases. And then once we start seeing the frequencies of each functional group, you'll see that they land between 600 and 4000. So these are the frequencies that match the frequencies of covalent bond stretching and bending vibrations. So we'll learn how IR affects molecules. So what does frequency depend on? So if you look at each individual molecule, you can actually treat them as springs. So if you remember from physics class, you have your spring constant, which is from Hooke's law, right? F equals kx, or k is the ratio between force applied and the distance traveled by a spring. So we can simplify the model by thinking of atoms as springs. So frequency, it actually depends on that k constant and mass. So we can say that frequency is directly proportional to the strength of the bonding between the two atoms. So frequency is proportional to k. But frequency is also inversely proportional to the reduced mass of the two atoms. And that's by a square root. So some trends, as the atoms become heavier and as the bond between them gets stronger, you can see some trends. So frequency decreases with increasing atomic weight, right? From H to C, frequency decreases, and from a single bond to a triple bond, frequency increases. Right, frequency increases with increasing bond energy. So increasing bond energy, frequency increases. So this is stretching. So if you have this atom and this atom, the bond between them is constantly stretching and being compressed as well. They're bouncing right towards each other and away from each other. But infrared radiation is largely thermal energy, and it induces stronger molecular vibrations in covalent bonds, which can be viewed as springs. So if you bombard this system with energy, this bond is going to more quickly be stretched and compressed. So it's like you're applying some force to a spring, and so it's going to quickly bounce up and down. But that's not the only kind of force that a bond can experience. Covalent bonds can vibrate in several modes, and they include stretching, rocking, and scissoring. But the most useful bands in infrared spectrum correspond to stretching frequencies. And there can be also several kinds of stretching depending on the molecule. But if you have a water molecule, you have symmetric stretching. You also have anti-symmetric stretching. As this hydrogen is being pulled towards the oxygen, this hydrogen can be pushed away from the oxygen. And then you have some bending, right? So the dynamics of a molecule can be plenty. A lot of trajectories can be taken by each atom. So IR spectroscopy. The radiation does not have enough energy to induce electronic transitions, as you see with UV. UV is higher frequency, right, than IR. If the frequency of the radiation matches the vibrational frequency of the molecule, then radiation will be absorbed, causing a change in the amplitude of molecular vibration. So if you have studied these systems, you can map springs with their amplitude. So if it's a short amplitude, the distance that it travels as it bounces up and down is shorter than if it has a higher amplitude. IR spectra are most commonly presented as percent light transmitted through a sample as a function of the wavelength or energy of the light. So the spectra are not really telling you much about, or they are telling you about the absorption, but they're mapped as the transmitted light. So not the light that is absorbed by the molecule, but the one that is transmitted. So the one that the energy that is not absorbed and instead is being detected by a detector. So it's sort of like colors. So black absorbs all the light, right? Therefore, if you had some sort of system that will tell you which ones are not being absorbed by black, you wouldn't see anything. So the samples that absorb all of the IR light will give a spectrum with a horizontal line near the bottom of the spectrum, because there's nothing that is being transmitted through the sample. So the real difference between transmission and absorption. When a chemical sample is exposed to the action of IR light, it can absorb some frequencies and transmit the rest. Some of the light can also be reflected back to the source. So you have that source from IR hitting the chemical sample, and then you have some light being reflected back to the IR source. But this is the main light that we're going to detect, and that's the transmitted light. So this is our absorption mode, which is the one that we don't really look at. We have frequency here, and this is going to tell you which kind of functional group you have. and this is how much of that is, like how strong that is. So it'll give you more evidence about that functional group. But this is the one that we look at. So as you can see, it's the inverse of the absorption. This is the most commonly used representation and the one found in most chemistry and spectroscopy books. Therefore, we'll use this representation. So the classification of the bands. IR bands can be classified as strong, medium, or weak, depending on the relative intensities in the infrared spectrum. A strong band covers most of the y-axis. So this is weak, this is medium, and this is strong. So you can already be thinking about what sort of property does a functional group have that will give a strong or a weak or even a medium signal. So these are some of the functional groups that do so. So a carbonyl functional group will give a strong signal because of the polarity between the C atom and the O and the oxygen atom. Whereas this will be medium because the polarity is less and it's also a very strong, a stronger bond. But this will be the weakest or one of the weakest because you have a strong bond, but you also have the same atoms here. The difference is that this is an asymmetric alkyne. What that means is that this carbon is bonded to a methyl group, but this carbon only has an H bonded to it. So then they're not symmetrical, and their stretching is going to be asymmetric. If you remember a few slides back, this creates a polarity, and so there's going to be more absorption or less absorption from IR. That is going to be therefore more transmitted and be able to be detected. So infrared band shapes come in various forms. Two of the most common being narrow and broad. So this is very narrow, such as with OH bonds, and also carboxylic acids, which have an OH bond. So IR is the most useful in providing evidence of functional groups without that much work, without thinking too much as with NMR. However, IR can also provide a molecular fingerprint, as we'll see. If two pure samples display the same IR spectrum, it can be argued that they are the same compound, except for isomers and stuff like that. IR does not provide detailed information or proof of molecular formula or structure. It provides information on molecular fragments, specifically functional groups. So if you have a sample, you can easily say what kinds of functional groups there might be there. So it's just like a very raw, very preliminary report for your sample. So you have to couple it with other techniques. So the fingerprint region, it's what it's called. So from 1500 to 400, the vibration frequencies are affected by the entire molecule. So you'll see like a bunch of signals here that are hard to interpret. So you would do that as you get more exposed to this technique, or with a machine, with a computer help. So again, this is the fingerprint region, and it's kind of hard to interpret. And it reads like C to C bonds and CO, which are pretty hard to interpret. So we'll focus our analysis here from around 1600 to 4000. So again, if you want to go to grad school, if you want to do forensic science, which they still use this equipment, especially I think there's a handheld version of it. You should probably memorize the regions for each of these. So the typical IR absorption range for covalent bonds is 600 to 4000. So again, from here to here. So an example, a sharp band around 2200 to 2400 would indicate the possible presence of a CN or a CC triple bond. So right around here. the IR spectrum of alkanes, you sometimes can have two signals. For example, for hexane, you will get some CH bending. So this H, imagine it going like this, like a pendulum. And you have stretching, which can be like this. Right, so for alkanes, it will appear mostly at 3000, around here. This will be the stronger bands. These will be the weaker ones. But besides the presence of CH bonds, alkenes also have medium bands, which are from their pi bonds. However, this band could also be obscured by the broader bands appearing around 3000. So the CH bond strength stretch will appear around here, but again, it can be obscured by broader bonds in 3000, as we'll see. So this spectrum shows the band appearing around 3080, this one, but it can be obscured by alkanes, right? The most prominent band in alkynes corresponds to the carbon-carbon triple bond. It shows us a sharp, weak band at about 2100 centimeters inversed. The reason it's weak is because the triple bond is not very polar, but like I mentioned earlier, in some cases with highly symmetrical in highly symmetrical alkynes, it will not show due to the very low polarity of the triple bond, or there should be no polarity. It should be a non-polar bond. However, terminal alkynes, that is to say the triple bond is at the end of a carbon chain, you will have an sp carbon. Therefore, they may also show a sharp, weak band at about 3300 inverse centimeters. Internal alkynes, that is those where the triple bond is in the middle of a carbon chain, do not have CH bonds to the sp carbon and therefore lack the aforementioned band. So let's see. So you have octine, and this is the triple bond C stretch. But as you can see, it's terminal, so you can see a weak band. Here you have the CH stretch, which is stronger, right here. And you can see it because it's terminal, again, so it's asymmetric. However, with 4-octine, the alkyne is in the middle of the molecule, so there's no stretch here, and there's no stretch here. But you have the alkane CH, so these CH bonds. You can see them here. Nitriles, however, now we jump to nitrogen-containing compounds. They appear 2250. So again, nitriles are a C atom connected to a nitrogen via a 1 sigma bond and 2 pi bonds. You can see it here. So it's quite a prominent band. Then you have the IR spectrum of an alcohol. This one is very broad, as we mentioned before. 3000 to 3700. So aldehydes and ketones. So to know these, they'll show a similar signal. They'll both show the C connected to the O, the carbonyl bond. So they'll always show 1700 and 1720. This is because of the highly polar carbonyl bond, and it's difficult to miss. But because the aldehydes also contain a CH bond to the sp2 carbon, they also show a pair of medium strength bands positioned about 2700 and 2800. These bands are missing the spectrum of a ketone because, again, there's no CH bond in a ketone. So let's see. So you have butyraldehyde. You can see the CH, or rather the carbonyl stretch with the CH, and it spans this portion. However, in heptanone, which is a ketone, you have it does not appear, right? The COH stretch is absent. But in both cases you see the carbonyl stretch, right? So in both cases it's here. This shows that you're missing the CH stretch on the carbonyl side. You still have the saturated CH stretches, but you're missing the one that would be around that carbonyl carbon. For carboxylic acid, you're combining the OH bond and the CO bond, so you also get a broadening of the OH. So it's like it was a carbonyl, but it's also broad because you're combining both signals. Finally, we have amines. Actually, not finally, but towards we're heading towards the end. So you have an NH stretch, which is here, but is not that prominent because of the polarity. And again, you have your saturated CH stretch, which appears in the same region. This is the fingerprint region, and it's hard to interpret. So primary amines have two NH bonds, and they typically show two spikes that make this band resemble a molar tooth. So this portion. Secondary amines have only one NH bond, which makes them show only one spike. Oh, okay. So this is actually the secondary amine. So yes, you can see N bonded to carbon chains and one H bond. So finally, tertiary amines have no NH bonds, and therefore this band is absent from the IR spectrum altogether. And then you have the amide, which is the carbonyl bonded to an amine. So the amide functional group combines the features of amines and ketones because it has both the NH bond and the CO bond. Therefore, amides show a very strong, somewhat broad band at the left end of the spectrum. So you have your NH stretch and you have your CH stretch. So it's kind of like, again, you're combining the carbonyl with an amine signal.